Belén, si me ayudas por favor con el acceso, te lo agradezco.
Sí.
Gracias. Welcome everyone. Thank you for joining us today. We will start around in 1 minute, so thank you for being here. So I think we're ready. Thank you everyone for joining today's webinar. We're starting right now. Today's ISFE webinar is entitled Microstructural Approach for Healthy Food Matrix Design by Professor Pedro Bouchon. Our speaker is professor at the Department of Chemical and Bioprocess Engineering at Pontificia Universidad Católica de Chile. He directs the Food Structure Design Laboratory, where he focuses his research on the design of food structures in a controlled manner based on specific formulations and or processes. The study includes the evaluation of the bioaccessibility and bioavailability of compounds of interest in vitro or in vivo, both in model systems as in food matrices. In addition, the study covers the integration of various microscopy techniques and includes, as fundamental part, the use of advanced image analysis programs to obtain quantifiable information on the structures studied. He has published nearly 50 Web of Science publications, and his work has been disseminated in more than 100 presentations at conferences in the area and has received 18 awards for quality of research and training of graduate students. He's also editorial board member of Food and Bioproducts Processing, Food Structure, and the CITA Journal of Food. His link with industry is relevant. He completed a sabbatical year at Nestle Research Center in 2015, where he joined the Food Structure Design Group and keeps working with Nestle R&D Center in India. He's also an entrepreneur who has developed a company to produce low-fat, tasty and nutritious vegetable snacks based on a protected technology he developed. Since 2017, he acts as Vice President for Research of the University. Before we start, please remember to mute your microphone during the presentation. If you have any questions through it, you can either write them on the chat so that you do not forget them at the end, and you can ask them directly to our speaker, or you can read them out loud. I can read them out loud for you. Again, thank you so much. It's a pleasure, Dr. Bouchon, for having you here today with us. And now the audience is totally yours. Thank you, everyone.
Thank you so much, Dr. Viridiana Tejada, for this kind introduction. And I would like as well to thank particularly Dr. Jorge Beltichanes and Dr. Keshava Niranjan, who kindly invited me to be part of this webinar series. So I will now share the screen with you so I can address the topic of today, which is, as Viri was explaining previously, microstructural approach for healthy food matrix design. I'm a professor at the Department of Chemical and Bioprocess Engineering at Pontificia Universidad Católica de Chile. And this is where I do my research with students, mainly at graduate level. Today I will guide you through the microstructural approach that I've been using in order to design food which can fulfill demands of very well informed and increasingly informed consumers, and as you know, whose needs and queries are readdressing the traditional from far to fork approach to a rather direction leading from the fork, that means the consumer, and the design that they want us to produce in order to fulfill their demands. And this has really made an important change in the food production chain, whose main challenge, I would say, during the first 50 years of the last century were mainly addressed to food processes, and it's still very important, certainly food process. But nowadays, I would say that this is directed through an interdisciplinary approach, really to focus extensively and intensively in food product design. And certainly food processing is a big part of this approach. But I just wanted to emphasize, because this is really one of the aspects that I've been focused on lately. And I can depict in this diagram, based on a diagram that was developed by Professor Jose Miguel Aguilera, that somehow shows how important these topics from an engineering perspective are becoming. And why structural approach is so important, because most important and relevant changes at the occur at the microstructural level, and finally they are expressed in the characteristic or macro properties of the food that we're intaking. But really the relevant structural changes from my perspective occur at the microstructural level. And it's very important and interesting to understand how we are able to develop that structure and how this structure can be deconstructed, which occurs while we are eating a food. And there are two very relevant aspects of this food intake, which I'm addressing through an interdisciplinary approach lately, interacting a lot with biological sciences and nutrition and medical doctors as well, in order to understand how specific compounds that are in the general structure through the gastrointestinal tract are liberated and thus become bioaccessible, and thereafter how these compounds that are liberated and become bioaccessible are incorporated into the bloodstream in order to reach the specific site of action. So I would address some of the aspects as well that have been focusing on through this interdisciplinary approach to try to understand not only the characteristic of the microstructure that leads to the macro properties that are finally expressed and are finally define the acceptance of consumption of different consumers, but also how the compounds become accessible and how they finally become bioavailable to human beings. So the talk will consider these three aspects. First, I will address the microstructural approach in product formulation. Then I will, through examples, I will illustrate how natural attributes may be preserved during processing. And thereafter, I will highlight some aspects that we have been working in our group, which focus on this food product design for better nutrition. And I will come back to this diagram all throughout the presentation to illustrate some specific points. So let's concentrate first in the food production chain. The food production chain means that we are going to address interest in this horizontal axis, and I highlight this first part as understanding. And understanding means to really understand how things happen during processing of a particular system. And I will start with deep fat frying, which is a unit operation that I have been working extensively during the last decades. In this diagram, you see the transversal section of a food, of a thick food, like a French fry, while it is immersed in oil at a high temperature, 160, 180 degrees Celsius. You can see that once the food gets into the oil bath, it will heat up on the surface, and then water will begin to evaporate. And as this process continues, the evaporation front will move towards the interior. And this will lead to a composite structure composed by a dry, porous, and crispy outer layer, denominated crust, and the moist and cooked interior, denominated core. This is what happens in a thick product. A thin product is very similar. The unique difference, as you must guess, is that finally, after the aberration is maintained, the product becomes just a single crust. That means a dry, porous, and crisp structure, similar to the crust. And what I mean by understanding is through different kinetic experiments that have been developed together with the microstructural approach that I will emphasize afterwards, we have been able to demonstrate within the group that as this evaporation of water is so intensive, the bubbling is so intensive during the deep fat frying that it really precludes and prevents oil to penetrate during the process, during the immersion. And we have been able to demonstrate that it mainly occurs upon removal of the food from the oil bath. And the oil layer that is deposited on the surface is finally absorbed within the porous structure once the product is removed from the oil. Some of the oil will drain, but some of the oil will penetrate within the crust as the vapor pressure decreases and the porous structures allows the oil to get within the structure. So thank you to this kinetic experiment, plus the addition of other observation tools, like the one I mentioned here, I have been able to really, and with the group and with my students, certainly my very important and relevant master and PhD students, we have been able to keep on understanding what's going on. So here I introduce you to a process miniaturization, which really allow us to carry out in situ observation. It means that this unit operation that appears here, like frying, is reproduced under the lenses of the microscope, thanks to a stage that can be heated in a controlled manner. And here we have a vacuum pump because in the system I have, I can also introduce vacuum. So I can really see what happens to the different components that I'm processing in this miniaturized system through the video camera online, and just being able not only to specify what happens to the structure, meaning it seems that cells shrink, but I can quantify the structure and be able to correlate it with the processing condition of interest. So basically, what I do is I carry out this little unit operation within the lenses of the microscope. Certainly, it's not the real unit operation. Here I need to deal with very little amount of product, but it can allow me to really develop in situ online observation non-invasively. And I highlight the non-invasively because most of the microstructural techniques that I develop within the group are aiming really to observe the structure non-invasively. I mean, another possibility would be to fry the sample, then to cut a section, and then to observe under the lens of the microscope. But this sometimes can become very invasive, because even though the microdome that can be used can be really, really sharp, at the end of the day, you are physically distracting the structure, and you can, at the end of the day, be observing the resultant of the manipulation of your sample and not really the structure that was originally obtained after processing. There are several precautions that you can take, and of course, you can really reduce the artifacts, but still it's possible to have some artifacts. So this is why I try really to develop microscopy techniques that allow me to observe in situ with minimal intrusion, like this one. This will be a unit operation, which is not exactly the same as it would happen in normal industrial conditions, but it allows me to obtain information like this one. I can follow in real time as I hit the sample. For instance, this is a little potato tissue that was immersed within a lens that contained a little amount of oil, under the lens of the microscope, and I can see as the temperature is increased, how the circularity of the cell decreases and how the area decreases as well as the cell is shrinking. These are the sort of observations that I also use to really understand what is going on, to really understand what is happening to the cell. Are the cells really breaking during heating, or are they just shrinking, and so forth? And I try to complement this observation with other ones. For instance, I can try to understand what happens with starch gelatinization. We use DSC, of course, and we use other techniques, complementary one. But it's really appealing to me to try to understand what happens to the different components in situ. So here, for instance, you can see what happens with starch granules when you heat them up in a system like the one I just referred. You can really see, if the system is very well tuned like this one, what happens through the heating up in the presence of water, of course, liquid water, how the starch granules become to swell and how finally they gelatinize. And this can be used, for instance, to not only to understand what happened with the circularity of the granules and so forth, but you can determine the degree of starch gelatinization in different systems. For instance, when you just mix starch, native starch in water, or with carrageenan, or with sucrose, and you can understand what happens to the system. And this can also really give you some additional information that allows you to understand what happens during this process. Similarly, another system that was developed by another PhD student, Pablo Cortés, the previous was by Teresa Molina, is in situ observation using glass micromodels. Yeah, also to understand what happened with the vapor escape during frying. So that's why Pablo developed this network that it's a very well conceived networks that summarize the porosity and the pore distribution that you would encounter, for instance, in a potato tissue. So he developed a system where he was able not only to develop this glass micromodel filled with water, but he was heating it up in an oil at a certain temperature in order to observe what happens with the empty of the pores, how the water vapor really leaves out the structure, and how the oil gets into the structure, to try to understand if those hypotheses that we develop in our kinetic determinations were consistent with these microstructural observations. And here you can see that when you heat the system, you can really see how the bubbles escape through the microchannels as frying progresses. Yes. And once you remove the micromodel from the oil bath, as I showed previously, you can also understand what happens, as you can see in this image, as oil penetrates within the structure, was the micromodels start to cool down, the vapor pressure is reduced, so the oil is able to penetrate within the structure, and towards the end of the process, you can see how the vapor really cools down and really stops the process from including additional oil. And thanks to this, we were able really to define like really penetration fronts of the oil within the micromodels and try to understand how this phenomena of oil absorption during cooling with different porous structure could be developed and occur. And thanks to this knowledge, it is possible to try to understand how to develop additional understanding through the development, for instance, of moving from problems where you can understand how oil is transferred within the structure, how the evaporation fronts start to move, what's the speeds at the rate of crust formation, and then to understand, for instance, which are the conditions of vapor pressure that needs to be fulfilled in order to allow the oil to penetrate within the structure upon cooling, or understand what might happen with oil drainage once you remove the food from the oil bath. So this first part, I wanted to let you know how with these different approaches, it is possible to try to get an understanding about what's happening in this unit operation. And from the microstructural perspective, of course, we do develop additional things, because one of the aims that I've been pursuing during my research is try to really maximize the quality of the food that is being processed. So here you have a cross section where you, once again, you have the crust. And what happens to the crust? Starch is going to gelatinize and it's going to dehydrate afterwards. You will have non-enzymatic browning, which is desired by consumer, compounds degradation that we should aim to avoid, water evaporation, and then we will have oil uptake. And this all will happen in a system at high temperatures, which will induce oil thermal degradation. Vapor is going to get within the oil bath, so, and this will produce hydrolysis. So this will degrade furthermore the oil, and then of course you will have oxidation. So it's not only important to understand what happened to the structure during the processing and formulation, but also what happens to the quality of the food. And certainly, if you are able to control, for instance, the temperature and the oxygen, you will reduce the rate of the chemical reactions, and you might be able to really improve, for instance, the quality by reducing the compounds degradation. What happens in terms of some metrics that we usually use, for instance, measuring temperature, conductivity, heat capacity, and so forth. So we'll have that on the surface. The oil will be at the most at 170 degrees Celsius, which is getting closer to the oil bath, depends on the temperature of the oil, of course, but it will be just a little bit lower than the oil temperature. Then you will have this area, which is the crust, which is where you don't have any more liquid water. So it will be at a temperature between 100 and 170 degrees Celsius. The waterfront will be at 100 degrees Celsius because it's the temperature a little bit more because of the solids that are present, but around that temperature. And it will restrict, yeah, it will be just at this temperature, and this temperature will be sort of maintained whilst the evaporation front moves towards the interior. And then inside in the core, you have a maximum temperature of 100 degrees Celsius, because otherwise the water will be evaporated, and you will have liquid water. And this is very important to understand, because this will induce, for instance, dehydration and compounds degradation. This will, for instance, affect the laminar lamella, and this will sort of allow the cells to move more smoothly and softly from each other, and to provide this mealy texture that you have within the structure and so forth. So temperatures are very important, as well as the state of water, water vapor, liquid water. So thanks to this understanding of the temperature, you can really, through formulation, which is another aspect I work a lot within the group, to develop different structures. Once you understand what is happening there, you know, what the effect of pressure, temperatures, I know shear forces in different domains, and particularly now in frying, many of the aspects are related to pressure and temperature. So as oil absorption is a surface phenomenon, as I explained you before, the surface roughness is very, very important. If the surface is smooth, the oil will drain quite easily. If the surface is rough, it will drain with more difficulty. And at the same time, it will not only affect oil drainage, but also it will define as well the available space for oil deposition. And then the inner part of the crust will be defined by the porosity, by the pore size distribution, finally the pore network that it's developed within the crust. And this will also define, on the one hand, the permeability to oil suction, and as well, depending on the porosity, the available space for oil deposition. So because of this aspect, it's very, very important to understand and to try to characterize the crust, and particularly the surface. So there are several structures that can be developed. Here I show you what happens, for instance, with structures that have been developed with 8% gluten, 12% gluten. we were developing specific formulation rather than using flour as such. We were mixing gluten and native starch in order to have a controlled proportion of our ingredients. We might be using methyl cellulose and so forth. We might be using potato flakes with methyl cellulose, potato flakes with native starch, and so forth. Yeah, and to try to understand what happens with the different surface with respect to oil drainage, to the permeability, and to the characteristics of the final product. And in order to evaluate the surface of the different structure that we develop, Dr. Carolina Moreno and Professor Chris Brown, together with the Polytechnic Institute in the United States, developed a technique that allow us to really characterize the surface of the structure using a laser scanning microscope. This is not a confocal, it's a laser scanning microscope. Through a laser, you can really follow the surface of a certain structure. And you can obtain really an elevation map of the different protuberance to try to understand what is the roughness of the structure. But as I said previously, one of our aims is to characterize and quantify the structure. So to do so, they develop what is referred as an area scale fractal analysis. So they cover the surface of the structure using different triangles, referred as triangular patch. And what they do is they measure the surface that is covered through the triangular patch over the projected surface. And they repeat this exercise with triangular patches of different sizes. A big triangular patch will really cover the whole surface, but when you use much smaller triangles, they will be able to penetrate within the protuberances that you can encounter on the surface of the structure. So it will give you an idea of the roughness. So if you have a very rough surface, this surface is going to be much bigger as if you had a very smooth surface using the same triangular patch. So following this understanding, we measure the relative area of the total area of patches over the projected area, and we repeat this exercise using different triangle sizes. And here is an image of what we sort of developed. Is you are reducing and reducing and reducing and reducing the size of the triangular patch, and as much as you reduce it, the triangular patch will be able to get into the protuberances, and therefore the relative area will increase. I will repeat this. Okay, so once you are reducing the size of the triangular patch, it can really penetrate within the different protuberances, and therefore you will have a relative area that will increase. So for a certain threshold, for a certain log of observation, for a certain size of triangular patch, a rougher surface will be the one that have a higher relative area. And thanks to this, we are able to understand the differences in roughness of different structures, basically. So thanks to this, we were able to correlate the relationship between the relative area, meaning more rough surface, with the oil content. And we clearly identified that there was a correlation between the protuberances, the roughness of the surface, and the total oil content that was observed within the structure. This is a correlation that we developed for the gluten starch matrices. And we had another correlation that was obtained behaving in a similar way with the structures that were designed and formulated using potato flakes. And clearly, even though there is a correlation between roughness and total oil content for both product categories, certainly there are other factors such as the inner microstructure that might explain the difference between, or the surface tension and so forth, that might explain the differences between the two matrices. So what I want to show here is that the rationale works. It is possible to quantify the surface roughness, but there are many times other additional factors that need to really be understood in order to develop and to design particular food products. So I want to focus a little bit more about processing and explain a little bit the work that I have developed with respect to vacuum frying. So the use of vacuum, most of you have used it many times, or at least understood it at undergrad level, mainly, or also graduate level. And we understand that once we reduce the pressure, we reduce the boiling point of water. Okay, so the idea is to use this concept during processing. Why? Because if you use vacuum, you will be able to dehydrate the sample at a lower temperature. So you will reduce the oil thermal degradation, and you will reduce the presence of oxygen. So you will reduce oil oxidation. You will not be able to avoid oil hydrolysis, because basically frying is a dehydration process, but you will be able to control these two aspects. And if you control these two aspects, you will be able to reduce degradation and maximize quality. So this is what we have developed together with Dr. Veronica Dweck and other students as well who have been working here. And here you can really see what happens with different products when you control process parameters. These are raw materials, and these are the characteristic of carrots, of potato chips, or apple chips that we have been able to obtain after complete dehydration up to bubble end point, 2.5% moisture, by reducing the vacuum, reducing the pressure using vacuum. And this has allowed us to reduce the frying oil temperature up to around 100 degrees C, much lower than what might occur in normal industrial frying operation. And therefore, we are being able to really preserve not only the current, the color, but also the compounds of interest, which are very much related, of course. So, and at the same time, we have been trying to understand what happened with this original structure with respect to the bioaccessibility and the bioavailability of compounds. So let me talk a little bit about starch. Yeah, starch, as you know, needs temperature and liquid water to gelatinize. And this is very important, not just temperature above 60 degrees C and so forth, but liquid water. So if we reduce the working pressure, we reduce the boiling point of water. That means that the evaporation front, instead of being at 100 degrees C, we can control it depending on the pressure. But for instance, in this example, I can control it by reducing the pressure and to define that the evaporation front and the water will evaporate at 45 degrees C. And let's say I will fry at 115 degrees C. It means that the crust will be within this range of temperatures. And the water, the liquid water, will be at the most at 45 degrees C. It means that we will be able to control the temperature to a very precise condition. So vacuum will impair starch gelatinization. Why? Because here you will have liquid water, but you will not have enough temperature to induce starch gelatinization. On the other hand, here you will have the temperature. You will have more than 60 degrees C, but you will have you won't have liquid water. You will have steam. Certainly, some gelatinization will occur, but it will be highly limited. So we will be able to reduce starch digestibility if we consider these operation conditions. But at the same time, it's important, we will limit structure formation too. If we process structure that has been provided by nature, let's say carrots, potatoes, apples, this might not be a big deal. But if we are processing, let's say, a dough, this will be a big deal because you will not be able sometimes to form the structure that is needed. So it's something of concern. So considering this rationale, we have been I've developed different concepts, and one of them is well, by reducing the pressure, reducing the boiling point of water, reducing the processing temperature. And in order to compare the different processes, I coined a concept that I define as thermal driving force. And the thermal driving force means the difference between the oil temperature and the boiling point of water. And in order to compare a process under atmospheric conditions and a process under vacuum, I always use the same thermal temperature difference. It means that if I fry at 170 degrees C, the boiling point of water will be 100. it means that we'll have a delta T of 70 degrees C. So if I fry under vacuum at 45 degrees C with evaporation temperature, I will use an oil temperature of 115 degrees C. And in that sense, and in thanks to this, I will be able to have similar driving forces that will allow me to compare both unit operations. And then I will, in the following figures, I will use two concepts. The time to reach bubble endpoint, which is the requirement. We need to fry the sample until it gets a moisture of around 2.5% moisture. And then in order to compare both processes, I will say what happened at when it has elapses half of this time. So this is time of endpoint and this half endpoint. And beside this, I have used several microscopy techniques that allow me to understand what happens to the structure. What happens to the structure when I observe the structure under the lens of the microscope, and in order to characterize it and to be able to correlate it with the processing conditions. So I have used scanning electron microscopy, confocal laser scanning microscopy, and X-ray microscopy. And this work has been done with Dr. Ingrid Contardo and together with Dr. James from New Zealand. And thanks to this approach, I have been able to understand what happened with the structure during confocal laser scanning microscopy, try to understand what happens to the components while you are really processing them. So in order to avoid post-labeling during structure for the observation, what we have developed, we have used fluorescent dye in the water that is being used to produce the dough, and we have fried them in an oil that already contains night red. These are fluorescent dyes that are needed in order to observe and characterize the structure using confocal microscopy. So we have developed methods that allow us to introduce the fluorophores that are needed in order to identify the structure during the preparation of the dough. And this is something that is very interesting because we have been focusing a lot of trying to observe the compounds as they are structured, avoiding post-labeling. So these are some of the approaches that we have used that allow us, or during the dough preparation, to include the dye that is going to allow us to identify the dough matrix in confocal microscopy, and the oil will be stained with the fluorescent dye during the frying process. So the oil that we get within the structure will already contain the dye. So you will avoid post-labeling, and then confocal microscopy, as it uses optical sections and not physical sections, you will be able to observe the structure in situ with avoiding any physical distortion that can be induced through the cutting of the sample. And also we have used X-ray microthermography, and the X-ray microthermography allow us to characterize the inner structure of the sample just as it is by introducing the sample within the microscope, and therefore to be able to characterize the porosity of the different samples non-invasively. So these, as I referred previously, these are some of the approaches that we use in order to really observe the structure and not the resultant of sample preparation. So here we have what happens to the vacuum fried samples that were processed at the lower pressure, and that means at the lower temperature. So we were somehow restricting the degree of starch gelatinization importantly. So this is what happens to through half of the process at the end of the process. And we were able really to reduce significantly starch gelatinization compared to atmospheric frying, where nearly 100% of the starch gelatinized. This was reflected as well in the texture. Here we have the maximum breaking force, and we can really see that vacuum frying samples are much more brittle compared to atmospheric ones, especially when preparing a dough, like the one I just referred previously. So it's very, very important, as I referred before, that we are going to be able to reduce starch gelatinization, but at the same time, we will have a much more fragile structure. And this can be observed using environmental scanning electron microscopy, where we can really see what happened to the gelatinized starch within the structure as compared to the ungelatinized starch that forms really a discontinuous network in vacuum frying, which is very much related or directly linked, I would say, to the texture that we were able to measure using texturometry, as I previously referred. Also, through electron microscopy, we are able to understand what happens with the structure, as was understood and studied by Dr. Ingrid Contardo, that we can really see that it's much more homogeneous, the structure, when we are processing under vacuum conditions as compared to atmospheric, where we have somehow some layers that are very well identified in the structure, as you can see here in the scanning electron microscopy. With respect to confocal microscopy, I will not really get much into this result, but I just want to show you some ideas. This is, as I said, we include the label in dough preparation with the water that is used for dough preparation, and we have already the Nile red label in the oil, and so we fry them immediately containing those labels. We can really see that through image analysis, we can identify the pores which do not contain oil. We can identify the pores that contain oil. We can identify the whole porosity, and we can develop all sorts of measurements that can allow us to understand what happens with the different structure, where does oil deposit, where it does not, and so forth. And I just want to show you here that we can also work with different coordinates, color coordinates, in order to really induce the appropriate thresholds and really differentiate the structure. We don't need necessarily to work with traditional binarized images. We can also work with these pseudo color coordinates that can allow us as well to identify the different components within the structure. The micro CT, as I said, allow us to really observe the structure within the micro CT, and really without any intrusion. So we can understand what happened to the structure, what happened to the porosity, what happens to the voids, how they are distributed, and how this finally is linked to the processing condition and the formulation that you are working with in order to develop these new food products, as I show you in this 3D image video that was obtained by observing one of the different structures that we have obtained in our lab, in our equipment. And what we did again here, and was very much interested, those matrices that we fried them in oil with Nile red that we use for confocal microscopy, we observed them as well within the micro CT. And we were able to identify that Nile red also enhanced the image contrast. Because it sort of allow us to distinguish as well within the micro CT, yeah, a peak that could be identified and linked to the oil, and another peak that could be linked to the solids. So thanks to this, we were able as well to segment the images that we obtained through micro CT microscopy, and in this way able to obtain information, 3D information that's very relevant about what is the structure of the fried dough. We could, by thresholding, as I just refer, identify only the solids portion within the matrix, where the oil is deposited within the structure, what happens with the total porosity composed by those pores which are filled with oil and the pores that are filled with air, and so forth. And this also correlated with the distribution of the oil that we could encounter within the vacuum fried samples, as I referred previously, yeah? That allow us to really, as we have a much more brittle structure, to absorb more easily the oil within it, as compared to the atmospheric sample in this way. So this work as well allow us not only to understand what happens with the structure and with the oil within the matrix, but also I was referring this paper, but Contardo and et al. Also to try to understand what happens through in vitro measurements with glucose release in the different samples. And here we have, for instance, what happened with the rapid available glucose fraction and the unavailable glucose fraction in dough in the raw sample, as compared with vacuum fried samples that were fried up to half endpoint or up to endpoint, as compared to atmospheric fried ones. And we can really see that you can heavily reduce the amount of rapid available glucose, and you can reduce as well, you can maintain high levels of unavailable glucose in some vacuum fried sample as compared to atmospheric fried samples. And this is related to the degree of starch gelatinization, as in this sample you have a lower degree of starch gelatinization, and consequently you have a lower degree of glucose availability. And that's why we obtain this lower amount of rapid available glucose fraction. That means the amount of glucose that is available within the first 20 minutes, and the unavailable glucose fraction in those samples. And these experiments were developed as well in vivo through the feeding of rats under very controlled conditions, through, of course, all the ethical protocols of the university. And we were able, by examining blood samples in rats after 30, 60, 90, and so forth intake, we could see what happens with the curve when you are feeding the rats just directly glucose, and what happens when you're feeding them vacuum fried samples, those that we were obtained up to half endpoint or endpoint. You can really see that the peak is displaced and is much lower as the one that is obtained with glucose itself. And when you feed them atmospheric fried samples, the peak that is obtained is very similar to the one of the peak that is obtained in glucose. And the area under the curve and the peak is much more closer to the one that we were observing glucose, meaning I'm referring to a very strong relationship between in vitro experiments and in vivo measurements. This was done, of course, thanks to a very strong cooperation with the Faculty of Biological Sciences here, and all the setup that they have been implementing, and the training that Dr. Contardo received, and well, to develop those experiments. I would like to get closer to the end of this seminar by explaining you a little bit what we have done in formulation, and not just only what we have done in formulation, but also the immense potential that we have in the use of agro-industrial waste, and how through formulation we have been able to include some compounds of interest that can be obtained from agro-industrial waste, and how through the formulation as well and this microstructural approach we can also get additional knowledge about the benefits that you can produce using this approach. So what we did, once again, we mixed starch, native starch, with gluten in order to have a control model matrix, and we added to this polyphenols from olive leaves. Olive leaves are agro-industrial waste that is basically useless nowadays. So we decided to, thanks to the work that has been developed by Dr. Veronica Dueck, to obtain the polyphenols extract from olive leaves, to freeze dry them, and then to add them to the formulations in order to obtain matrices that are rich in polyphenols obtained from this agro-industrial waste. And what we did here, what she did here is that first she simulated the gastrointestinal digestion, and she uses CACO2 cells in order to obtain the in vitro bioavailable fraction. Okay, so basically here the stomach condition and the duodenal conditions were simulated, and this the sample was centrifuged, and the liquid fraction that was obtained here the polyphenols content were measured there in order to understand the bioaccessible bit, that means how much of this polyphenol extracts that we've added in the formulation after processing, after processing the samples were actually bioaccessible. And this liquid fraction that was obtained here finally was used to assess the transport through the CACO2 cells monolayer. And after the incubation period, the total polyphenols on both sides of the monolayer were measured in order to determine the bioavailable fraction of polyphenols in those fried matrices. So that's very interesting because we were able to assess in vitro the bioaccessible fraction, and then out of this bioaccessible fraction in vitro as well, the bioavailable fraction, that means those that were liberated, what happens if they, in this in vitro system, would either or not go through the CACO2 monolayer in order to obtain the bioavailable fraction. And what is interesting here is that this is what happens to the matrices that they process under vacuum. And this is what happened to the matrices that were processed under atmospheric conditions. So you can really see that here is the original content that you had in those systems after processing. After processing using an equivalent thermal driving force. That means a lower temperature of frying in this one, in this one, in this one, in this one. So you are increasing the oil temperature here. And this is the bioaccessible fraction that was obtained after the centrifugation that I referred to. So it means that most of the compounds of the polyphenols were bioaccessible, as you can see here. But then, and it's very important, the question is, well, of this fraction that was bioaccessible, how bioavailable it was. So we could see that it was extremely reduced, but still the bioavailable fraction that was obtained in vacuum fried matrices, because certainly as well related to the processing condition, as I referred before, was much higher compared to the fraction, the bioavailable fraction that was obtained under atmospheric conditions. So this is a summary of what we have been doing, and at present I just end up with this. We're still working, considering this approach, to try to understand the relationship between the food production chain and the consumer in different systems, working in baking, in extrusion, and in frying. And I will just very briefly refer to what we have been doing, we are doing here at present. So Yadira Zambrano, PhD student, she's working and studying the effect of moisture and extrusion parameters on the microstructural third generation snack based on rice flour, gluten-free flour, very important, and third generation. What it means, third generation? It means that after the twin screw extruder processing, you obtain a pellet, and which is not heavily expanded. And what is interesting of this is that afterwards you will be able to expand it in a different thermal equipment, let's say a microwave or a normal oven and so forth. So thanks to this, you are able to produce pellets if you control the processing conditions here. And that's why it's very important. The temperature is very important. The RPMs in the system is very important. The moisture, of course, that you will use. And you can adjust the conditions in order to have a rather non-expanded product here. And this is very interesting because you will make it available to many industries which might not have the technology, the extrusion technology, but they can really purchase the pellets, and on their own, they can further expand it. And also it can facilitate the transport because this will require much lower volume and so forth. So it's very interesting concept, the third generation snacks. So what she's working on, Yadira at present, she's understanding the relationship between formulation, processing conditions, pellet obtention, expansion through microwave heating, having a microstructural approach using different techniques, but notably micro-CD. And she's also working now with the addition of catechins, and thereafter she work as well with agroindustrial waste from grapes harvesting. So it's very interesting because it's the concept of circular economy again, and how we can really understand the relationship between formulation, processing condition, in this case, pellet obtention, expansion, microstructure, and so forth. Another PhD student, Jose David Torres, he's finishing his work to understanding the effects of soluble dietary fiber inclusion and starch digestibility, together with Dr. Dweck, a former PhD student that now works in the company. We are studying different systems by basically trying to understand what happens during baking in different laminated doughs, what happens when we include certain fibers like inulin, polydextrose, partially hydrolyzed guar gum, and so forth, and as well in this system, green tea polyphenols, and try to understand what happens with different outputs of interest. For instance, here we work in acrylamide production and trying to understand what's the effect of green tea polyphenols in acrylamide reduction, or what might be the effect of these inclusions in the bioavailability of glucose, rapid available glucose fraction or unavailable glucose fraction in the different system, and also to try to understand what happens with the microstructures once you are making variation in the formulation, to try to understand once again the relationship between formulation, processing condition, microstructure, and at the end of the day, the structural properties of the final matrix. Another work that is developed by Teresa Molina, who just finished her PhD. She was understanding and studying the effect of sucrose size, sucrose concentration, and as well as fiber inclusion, arabinoxylans inclusion, and so forth in the system, to try to understand what happens in rotary molded biscuits with respect to the characteristic of the final product, and the link between, again, microstructure, processing conditions, and formulation, to try to understand what happens with the system in terms of aeration, expansion, and finally, quality characteristic of the structure, again, using non-invasive methodologies that allow us to obtain quantitative information out of the samples to be studied. And the last example I want to refer to today is the work that is being developed by Pratiksha Garg. She works at present in Nestle in India, in the Nestle Development Center in Gurgaon in India. I started working with this group while I was doing my sabbatical in Nestle Research Center in Darche-les-Blancs in Switzerland. That's where I got in contact with this group, and I keep on working with them, trying to help them to understand what happens to the noodle characteristics during processing, and how we can develop alternative processing conditions that allow us to obtain similar characteristics in non-fried noodles, and what happens as well with the relationship between formulation, processing, microstructure, and flavor compounds release. So this is basically where we are developing at present with her. So as a summary, I expect that it was possible for me to illustrate how natural attributes may be preserved during processing overall, and that you were able to understand what I means by the microstructural approach in product formulation, and basically to give you some additional tools that can be instrumental for you in order to design food for better nutrition. So once again, I thank you for this opportunity. And of course, I would like to acknowledge all the students who have been working with me through the years, master students, PhD student, administrative support too, and certainly the financing of different agencies that allow us really to develop this state-of-the-art research in our country. So thank you so much for your attention, and I'm happy to answer some questions you may have. I will stop sharing the presentation now. Thank you.
Thank you so much, Dr. Bouchon, for sharing your knowledge with us. So let's start this, the question and answer portion of the webinar. Remember, if you want to turn on your microphone to ask the question, please. You can do it right now, or you can also write them your questions in the chat so that I can read them for you. By now, we have a couple of questions. I don't know if Jose wants to ask directly. If not, I can make it. I can read it for him. Is it possible to analyze the reaction of acrylamide formation in deep frying of potatoes with this technology?
Right. The acrylamide formation should be really assessed through analytical techniques. Okay. So here I presented some results that were obtained through these analytical techniques, and certainly these techniques can be used overall. But let's see, because it's not possible really to assess acrylamide formation with this, I would say, with these microscopy tools, okay? But they can really give you an understanding of what might happen of the result that you obtain using these analytical tools, of course, I think. First, as you know, acrylamide is very much related to Maillard reaction. So you can understand how to control the processing parameters that will reduce Maillard reaction, and through the reduction of Maillard reaction, you can correlate it with acrylamide formation. In the microstructure, you can think about some correlation. Color is usually used, certainly, but let's imagine that this might be as well related to some, I don't know, thermal degradation in the structure. And this could be at the end linked to the porosity development if you do not alter other conditions, of course. So you might get some inference between like processing, formulation, maybe the structure, and then the structure you will be able to link it to the acrylamide formation that you can determine through analytical techniques. But microscopy technique, I must say, might not be the best technique to assess acrylamide formation, but you can get additional insight that can complement the understanding of what might be happening in your system.
Thank you so much. Then I don't know if Dr. Niranjan wants to make his question.
Yeah, Pedro, fantastic talk. I really enjoyed it. I mean, you have taken a very reductionist approach and really gone micro, probably sub-micro, and you can go, I mean, nowadays techniques are available and you can go on very, very small scales. The question I have is, the phenomena that one observes on such small scales, are they representative? Because you're actually doing highly localized measurements. Are they representative of everything that's happening in a sample which is of the size, for example, the size that we eat? I mean, when we consume, yes, I'm sure we will be much healthier if we consume microscale and nanoscale samples, but we'll be very hungry. But I'm just wondering whether whatever we observe on such a small scale, is it representative?
Yeah, thank you, Niranjan, and really nice to talk to you as well.
Sure.
Thank you. Yes, let me try to elaborate because I think that your question is critical. It's critical. Through time, what I've been moving quite a lot in microstructural characterization is really to get statistical sounds measurement as much as possible. It means like, analyzing replicates obtained from different batch production, and then obtain or develop different measurements from one of the samples in order to have like pseudo replicates within one sample, one batch, and so forth, in order to really try to get sound and quantified information which is more statistically sound. As you know, I work in the editorial board of the food structure, and I think that many times people ask too much to an image. Too much. It's like, come on, it's true. I mean, and when we are so passionate about it, we can really see so incredible things and to develop so incredible theories. And I'm not saying that it's not good to really have this mind and really to open possibilities. Of course, it is very, very important, very, very important. But at the same time, you really need to develop sound statistical measurements. And I think that's the challenge that I see that have to go now on in the microstructural field, not just to use it as a complementary tool, but use it as much as possible as an analytical tool, okay? So that's first disclosure, and I think that will allow us to have a better correlation as well between this tiny little micro world and the structural properties. There are some techniques that can be used in bigger samples, okay? Micro-CT is an example, for instance. So micro-CT is an example. You really need to be very careful because if you use such a big sample, you can really reconstruct afterwards and so forth, but it will take ages, and then you really need to balance this. But there are some techniques that can be used at the macro, a bigger level. There are some others, and I really encourage people to use them, like traditional reflection microscopy. I'm a big fan of it. I'm a big fan of it. I mean, not everything has to be so micro. Not everything has to be like confocal or optical transmission microscopy or scanning electron microscopy. I would encourage people to really use like reflection microscopy, traditional reflection microscopy, which is like a magnification lens, and this can give you very interesting information. Probably you will have a lot of out of focus details sometimes, but I really encourage you. Then you can even increase. I really encourage digital images, like digital photography. Digital photography can also be very interesting as well to really understand bigger samples and try to get a better understanding more at the macro level. And then beside all this, I would say that usually what I try to do is really to correlate this aspect with other macro structural properties. For instance, texture. I use it a lot. Texture. I use it a lot. Color. I use it a lot. So sensory evaluation sometimes in order to try to understand as well the relationship because otherwise you really need to have a track of the system as much as possible in order to really make a better sense of the microstructural observation and the characteristics of the final product. Myself, I seldom use nanotechnology, observation at the nanoscale. Very, very limited. I always start mainly with micron above, because for the system and for the understanding I build, nanoscale can be useful. I've done studies of the surface of starch granules after freezing using atomic force microscope. It's interesting because you can really see the protuberance and it can give you an idea. But usually I work myself on the macrometer range above, and I would definitely encourage to develop new techniques. Here, there is a lot of playing what I show you here. I mean, it's a lot of trying and errors, and be brave in order to develop new techniques. And I would encourage new methodologies. We have very powerful now macro system which have a huge resolution. Even a mobile phone can be used. So I will not restrict this to the very limited scale. Thank you, Niranjan.
Thank you so much. We have a lot of questions, but I know we're running out of time, so I'll just try to make the last one. I'm sorry for those ones who wrote it and we didn't have enough time for you. Dr. Torres, if you want to make your question.
It was not a question, it was just a comment
on
what Pedro was saying, that I mean, the best confirmation is that you're using your information to create a model, make predictions what manipulation you're going to do to the process. If all your predictions work, you're likely on the right path. I mean, that's for me the ultimate confirmation of when you can use it for something real.
Fantastic. Thank you, Jose. Nice to talk to you as well.
Yeah, and hopefully I'll see you soon when we can travel again.
Hopefully.
Well, thank you so much. Thank you everybody for your interest, for your questions, and thank you again, Professor Bouchon, for this exciting talk. Remember this talk will be, it has been recorded and it'll be posted on our YouTube account, ISFE webinars, and keep tuned and check our website, Facebook page, and we also have an Instagram account for information regarding our next presentation. Muchas gracias, Dr. Pedro. Y bueno, un placer tenerle aquí con nosotros. Thank you, everyone.